Hi everyone, today I'm going to discuss the fit of my best performing classifier for the diabetes dataset. I built a full end-to-end classification pipeline using XGBoost as my final model. The workflow includes data cleaning, missing value imputation, handling categorical variables, class imbalance treatment by smooth stratified 5-cloud cross-validation, hyperparameter tuning, and decision threshold optimization. First, I focused on improving prediction quality through precision. I removed the duplicate rows from the training set to reduce noise and prevent the model from learning repeated patterns. I handled missing value using median imputation for numerical features and the most frequent imputation for categorical features. Clean precision improves both model stability and generalization performance. Next, I addressed the class imbalance. If the imbalance is ignored, the model tends to predict the majority class too frequently, resulting in a high accuracy but poor recall for diabetic patients. Since patients with diabetes who are missed call delay diagnosis and treatment, recall is very important. I use modes with each cross-validation to oversample the minority class during the training. This improved the recall and significantly increased the F1 score compared to a baseline without imbalance handling. Before selecting XGBoost as my final model, I considered 3 model types: logistic regression, random forest. Logistic regression is interpretable and stable, but it may underfit complex non-linear relationships in health data. Random forest can capture nonlinear intersection and is robust, but it may not always maximize the F1 score under imbalance. However, XGBoost can capture nonlinear intersection effectively and include the built-in regularization to control overfitting. In cross-validation, XGBoost achieved the highest F1 score among the model I evaluate. To further improve performance, I turned hyperparameters such as the number of trees, learning rate, maximum depth, and the L2 regularization strength. This parameter balance model flexibility and regularization. Regularization helps prevent overall complex tree from memorizing noise. After turning, the cross-validated F1 score improved compared to the initial baseline configuration. Another important improvement was decision threshold optimization. Instead of use the default probability threshold of 0.5, I collect out of for the predict probability from stratified 5 for cross-validation and searched across threshold from 0.1 to 0.89. I select the threshold that maximizes the average cross-validate F1 score. For validation, I used the stratified 5 for the cross-validation instead of a single train test split. Stratification ensures that each fold preserves the class distribution. This reduces randomness from one lucky split and produces more stable F1 estimate. It also allows me to generate out-of-4 prediction, which provides an unbiased estimate of generalization performance. To access model fit, I examined the confusion matrix. In this context, a false negative means failing to identify a patient who actually have diabetes. A false positive means predicting diabetes for a patient who does not have it. Therefore, balancing recall and precision is very important. I also plot the ROC curve. The ROC curve shows the model's ability to separate diabetic and non-diabetic patients across all thresholds. However, because the dataset is imbalanced, I also plot the precision recall curve. The PR curve provides a clear view of minority class detection performance. The average precision score indicates that the model performed better than random guessing and captured useful signal in the data. If I had more time and resource, I would incorporate additional external health data to improve the predictive accuracy. For example, laboratory test results, lifestyle factors, and genetic risk indicators could significantly enhance the model. These variables often have strong relationship with diabetes risk and would likely improve recall and overall F1 score. All in all, I built an XGBoost classifier with careful precision, class imbalance handling, hyperparameter tuning, threshold optimization, stratified cross-validation, and a comprehensive evaluation using confusion metrics, ROC curves, and precision recall curves. Thank you.